There's a question NASA engineers still can't answer properly. Not because they lack the words, because they lack the answer. And that question comes from a probe launched into space nearly 50 years ago. A probe that was never supposed to last this long, never supposed to travel this far. And yet right now, as you watch this, it's still sending data from a place no human-made object had ever reached before. We're talking about Voyager. And what this probe has detected, what it keeps detecting, shouldn't exist. Not according to the laws of physics we teach, not according to the models that the world's greatest astrophysicists spent decades building. So either Voyager is sending us corrupted data, or our understanding of the universe is the thing that's corrupted. Hold on. Because what we're going to explore today might be the deepest challenge to modern physics since Einstein. And I say that without exaggeration, without drama. I say it because that's what the data shows, and nobody right now knows what to do with it. Before we go further, we need to agree on something. When most people hear the name Voyager, they think they already know the story. 2 probes launched in the 70s. They flew past Jupiter, Saturn, Uranus, Neptune. Stunning photographs. A golden record carrying sounds from Earth. A romantic, almost poetic vision of humanity reaching out into the cosmos. And technically, all of that is true. But what usually goes unsaid is that Voyager was never just a scientific project. It was a bet. A wild, almost reckless bet. 2 spacecraft, each weighing under 900 kilograms, were launched toward a part of space where nobody knew what was waiting. The hope was simply that they'd survive long enough to tell us something. And they survived. 47 years later, Voyager 1 is more than 23 billion kilometers from Earth. 23 billion. Take a second and try to hold that number. Light, which travels 300,000 kilometers every second, takes 22.5 hours to cover that distance. 22.5 hours. And yet, the probe is still talking to us. A signal traveling at the speed of light for 22 hours, picked up by the massive antenna dishes of the Deep Space Network, scattered across 3 continents, their enormous receivers pointed permanently at the sky. And that signal, fragile, stretched almost to nothing, impossibly faint, is saying something nobody fully understands. To make sense of what's happening, we need to talk about a place with no fixed shape, no clear boundary, no color. A place you can't see, but you can measure. It's called the heliosphere. It's the enormous bubble our sun creates around itself. A bubble of solar wind, a constant stream of charged particles the sun continuously ejects, stretching outward in all directions for billions of kilometers. This bubble is our home, not just Earth, not just the solar system. Everything we've ever known floats inside this invisible envelope, kept alive by the sun's breath. For decades, physicists built models to describe how this bubble works, how it interacts with the interstellar medium, the space between the stars. Not completely empty, filled with gas, dust, and extremely faint but real magnetic fields. These models were precise, elegant, internally consistent, until Voyager crossed through them. September 5th, 1977. That's the day Voyager 1 lifted off from Cape Canaveral. Actually, Voyager 2 had launched 16 days earlier on August 20th. But the trajectories were different. And Voyager 1 eventually pulled ahead. That detail, the fact that the numbering doesn't match the launch order, tends to get forgotten. Maybe it's a minor footnote. Or maybe it's the first small sign that nothing in this story is quite as straightforward as it appears. The original mission was planned for 5 years. 5 years to fly past the giant outer planets, photograph them, measure their magnetic fields, analyze their atmospheres. and then drift silently into the void forever, becoming a piece of mute metal tumbling through eternity. But the engineers at the Jet Propulsion Laboratory in Pasadena had underestimated two things: the durability of what they'd built and their own curiosity. When 5 years passed and the probes kept transmitting, nobody had the heart to turn off the receivers. They kept listening. They kept collecting. And slowly, over the following decades, a picture began to take shape. A picture that looked nothing like what anyone expected. Here's where things get genuinely interesting. To explain the first anomaly, we need to talk about something called the termination shock. That's the boundary zone where solar wind begins to slow down, meeting the resistance of the interstellar medium. Think of a wave rolling toward a beach, gradually losing energy before it disappears into the sand. Models predicted this boundary would sit at around 85 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. Voyager 1 crossed that boundary in 2004, at 94 astronomical units, 9 units further out than predicted. That's 9 times 150 million kilometers of discrepancy. Scientists nodded, adjusted their equations, and told themselves it was within an acceptable margin of error. Models are never perfect. Move on. Then Voyager 2 crossed the same boundary, at 84 astronomical units. 10 units closer than Voyager 1. Same sun, same type of solar wind, same interstellar medium. 2 probes, 2 completely different results. At that point, scientists stopped nodding. I want to pause here for a moment, because this is something we tend to gloss over when reading scientific papers. The numbers are cold, the publications are dry, and we miss what it actually means. Imagine you build a mathematical model to predict how a ball bounces off a wall. You've factored in speed, angle, mass, air density. You're confident in your calculation. Then you throw 2 identical balls at the same wall under identical conditions. One bounces back and lands 94 centimeters from your hand. The other lands 84 centimeters away. That is not a margin of error. That is a sign you've missed something fundamental about the phenomenon itself. And that was just the beginning. In 2012, Voyager 1 crossed something physicists call the heliopause, the true boundary, the absolute outer limit of our sun's influence. Beyond it, solar wind no longer blows. Beyond it lies the interstellar medium, the space between the stars. No human-made object had ever gone that far. To mark this historic crossing, NASA was watching for specific signals. It knew, based on its models, exactly what Voyager should find on the other side. The magnetic field should shift direction. The density of charged solar particles should drop sharply. And galactic cosmic rays, high-energy particles from other stars, other galaxies, partially blocked by the heliosphere, should spike suddenly. All 3 signals together would confirm that Voyager 1 had truly left the heliosphere. Here's what actually happened. Cosmic rays increased. Solar particles dropped. But the magnetic field did not change direction. For several months, physicists refused to officially declare that Voyager 1 had exited the heliosphere because that 3rd signal was missing. The models were unambiguous. Without a directional shift in the magnetic field, you're not in interstellar space. Then, in August of 2012, the magnetic field finally shifted, abruptly, all at once. Except it wasn't the right kind of shift. Not the one the models predicted. The magnitude had increased, but the orientation was different from what the calculations called for. NASA officially confirmed the crossing in December 2013. But internally, serious questions remained open. Very serious questions. I want to tell you about one person, not because scientific personalities matter more than the science itself, but because this story needs a human face to convey what these data points really mean, emotionally, intellectually. Don Gurnett, physicist at the University of Iowa, specialist in plasma waves, one of the key minds behind the PWSS instrument on both Voyager probes, the Plasma Wave Science Subsystem, a device designed to measure electrical oscillations in interstellar plasma. Gurnett is the person who officially announced that Voyager 1 had entered the interstellar medium. But what gets told less often is how he reacted when the data first arrived. Because what he heard, or rather, what he converted into sound from raw data, was something no one had ever heard before. A hum. A low, deep hum that slowly rose in pitch. It wasn't a natural radio emission. It wasn't a sensor error. It was a plasma oscillation. A vibration in the very fabric of the interstellar medium, triggered by a solar eruption that had sent a shock wave traveling billions of kilometers to reach the probe. This hum had a frequency of roughly 2,200 Hertz, which made it possible to calculate the density of the interstellar plasma at that precise location. And that's when physicists felt their first real chill. Not because the density was too high or too low, because it was stable. Remarkably, inexplicably stable. Identical to estimates made from Earth-based measurements taken years earlier, in a universe defined by motion, turbulence, quantum chaos at small scales. This level of stability was strange. Too clean to feel natural, or perhaps too natural for us to yet understand. In 2019, NASA published a study. Not an enthusiastic press release, a peer-reviewed paper in Nature Astronomy, signed by an entire research team analyzing data from Voyager 2, which had crossed the heliopause in November 2018 at 119 astronomical units from the Sun. And this study says something that honestly should have made front pages around the world. The transition layer between the heliosphere and the interstellar medium is far thinner than expected. Models had predicted a gradual transition zone, smooth, extended over millions of kilometers. Voyager 2 crossed that boundary in a matter of days. A few days to go from inside the heliosphere to outside in the interstellar medium. That means the edge of our solar bubble is almost sharp, like a membrane, like a wall. Not gradual, not blurred, abrupt. And no model had predicted that. No model at all. This is the point where things shift into genuinely uncomfortable territory, because we're no longer talking about a margin of error or a parameter adjustment. We're talking about the fundamental physical shape of our own heliosphere, not matching what decades of plasma physics and magnetohydrodynamics taught us to calculate. And if the shape of our own solar bubble is poorly understood, what do we actually understand? I want to sit with that question for a moment, because it's dizzying. We've mapped galaxies billions of light years away. We've detected gravitational waves from two black holes merging more than 1 billion light years from here. We've photographed the shadow of a black hole 55 million light years away using the Event Horizon Telescope. And we can't correctly predict the boundary of our own home. There's something deeply humbling in that. Something that should make us more humble, more curious, more attentive. But the real signal, the one at the heart of all this, arrived in 2020. When I say signal here, I should be precise. This isn't a transmission in the deliberate sense. It's a measurement, a detection. An electromagnetic footprint in the raw data Voyager sends across 22 billion kilometers of empty space. But this footprint persists. In 2020, a team at the Massachusetts Institute of Technology, led by researcher Stella Koch-Acker, who was then near the beginning of her career, published a fascinating analysis of plasma data from Voyager 1. What she found was this: the interstellar plasma hums continuously. Not chaotically, not randomly, regularly. A steady, low-level vibration, almost imperceptible but constant and stable. A kind of baseline tone, as if interstellar space had its own fundamental frequency. Some researchers began calling it the interstellar hum. And this hum is unexplained. You might be thinking, plasma oscillates naturally, fluids vibrate. What's so strange about that? That's a fair question. And the answer lies in the source. This hum doesn't match any known solar phenomenon. It isn't caused by the sun. Solar flares, coronal mass ejections, solar winds, all of those create plasma oscillations, yes. But they're discrete events, tied to specific bursts of stellar activity. What Voyager 1 is picking up is different. It's a permanent background signal, near constant. And it seems to come from everywhere, from the interstellar medium itself. As if the space between the stars isn't inert. As if that emptiness is breathing. I know that sounds poetic. But I'm speaking in concrete physical terms. Measurable oscillations, quantifiable frequencies. Not a metaphor. A real phenomenon. And we don't know where it comes from. We need to talk about the theories. Or, rather, a family of theories. Because faced with these anomalies, physicists have proposed several explanations. And each one, if confirmed, would overturn part of what we think we know. First hypothesis: the interstellar medium is far more structured than we thought. Not uniform, not homogeneous. Threaded with filaments, layers, regions of varying density that generate these oscillations through simple turbulence, like currents in an ocean producing surface waves even without wind. This is the most comfortable explanation. It doesn't challenge fundamental physics. It just says our picture of the interstellar medium was too simple, and we're learning it's more complex. But there's a problem. If the interstellar medium were as structured and turbulent as this hypothesis suggests, why is the hum so stable, so constant? Turbulence, by definition, creates variability. This signal is disconcertingly regular. Second hypothesis, more ambitious. An interaction between high-energy cosmic particles, galactic cosmic rays, and interstellar plasma. These rays travel at significant fractions of the speed of light. They pass through everything: stars, interstellar clouds, magnetic structures. And in passing through plasma, they may deposit energy in a very specific way, generating these background oscillations. It's a compelling idea because it connects two phenomena that were previously studied separately. But here too, the numbers don't add up. The energy needed to sustain a hum this constant over years of observation exceeds what the measured cosmic ray flux can reasonably provide. Something is missing from the equation. Something we haven't identified yet. Third hypothesis. The one people discuss in low voices in the hallways of physics departments. The one that doesn't get published in Nature yet, but comes up in conversations after conferences, over coffee, when the cameras are off. The possibility that the interstellar hum is an intrinsic property of the vacuum itself, not the consequence of some external phenomenon, not a byproduct of an interaction, but a fundamental characteristic of space-time at very large scales. A kind of permanent, universal background energy. If that's the case, then our equations for plasma physics, our models of interstellar space, our theories about electromagnetic wave propagation in vacuum, they're incomplete. Fundamentally incomplete. I want to pause on the word incomplete. In the language of physicists, incomplete might be the most frightening word in the vocabulary. Not wrong. Incomplete. Wrong means you start over. Hard, but clear. Incomplete means you've built something that works perfectly in certain conditions and breaks down in others. And you don't yet know where the line between the two sits. That's the real problem with Voyager. Its data is consistent with the physics we know, up to a point. And beyond that point, it challenges it. Not spectacularly, not in a way where you can point to one precise moment and say, there, that's where it breaks. But gradually, subtly, persistently, like a crack in a wall that's invisible at first, until you look carefully, and then it's there, and it's growing. In 2021, another publication added another layer to this mystery. 5 different instruments aboard Voyager 1, some of which have been operating for 44 years, which is itself extraordinary for electronics exposed to interstellar radiation, recorded a series of similar electromagnetic events. Brief pulses, repeated, spaced in a pattern that was neither fully random nor perfectly regular. Not like clockwork, not like white noise. Something in between. And this pulse pattern, at a cosmic scale, resembles something well known in fluid physics: intermittent turbulence. The kind found in rivers just before they turn fully chaotic. That zone where motion is still almost organized, but unpredictable eddies are starting to appear. Is the interstellar medium churning at a scale our models never anticipated? Perhaps. But then, what's heating that pot? There's a side of this story that almost never gets told. The engineering side. The human side. Voyager 1 currently transmits with a power output of 22 watts. 22 watts. Less than most light bulbs in your home. And that 22-watt signal, broadcast from an object 23 billion kilometers away, travels for 22 hours at the speed of light before reaching Earth. By that point, it's so faint that the Deep Space Network antennas must use extraordinarily sophisticated signal processing techniques just to distinguish it from background cosmic noise. And despite all of that, despite 47 years in space, despite radiation, extreme temperatures, zero maintenance, zero possibility of repair, Voyager 1 is still transmitting. Powered by 3 radioisotope thermoelectric generators running on the natural decay of plutonium-238, energy that decreases by roughly 4 watts per year. Current estimates give Voyager 1 a transmission window, lasting until somewhere around 2025 to 2027. After that, the power will be insufficient to run the scientific instruments. The window during which this probe can teach us something is closing, and we still don't have answers. This brings me to what's known as the Pioneer anomaly. Not the interstellar hum, not the heliopause measurements, something older. Something that was solved, or at least believed to have been solved, in the late 1990s. Engineers at JPL noticed something strange. Both Voyager probes, and also Pioneer 10 and 11, were decelerating slightly faster than expected. Not by much. A spurious force on the order of 8.74 times 10 to the power of -10 meters per second squared. A ridiculously small number, but unexplained. This anomaly troubled physicists for more than 30 years. Some proposed dark matter. Others, a modification of gravity at large distances. Some even suggested entirely new physics. Then in 2012, a team published a thorough analysis and demonstrated that the cause was thermal. Heat radiated asymmetrically by the instruments themselves created a microscopic recoil pressure. Problem solved. Everyone exhaled. Maybe too quickly. Because here's what didn't get stated clearly at the time. Yes, the Pioneer anomaly was explained. But the current Voyager data, the new measurements, the plasma hum, the abrupt heliopause boundary, the intermittent electromagnetic pulses, none of those are covered by that thermal explanation. These are different phenomena, measured by different instruments in a completely different context. And the fact that the Pioneer anomaly got resolved may have created a kind of premature relief. A feeling that Voyager's major anomalies were all explainable by minor technical effects. They're not. The interstellar hum doesn't come from radiated heat. Neither do the electromagnetic pulses, neither does the sharp boundary of the heliosphere. I want to mention another researcher, James Cordes, astrophysicist at Cornell University, one of the world's leading experts on the physics of the interstellar medium. In 2021, he made a statement that stayed with me. He said, and I'm paraphrasing, that Voyager's data shows the interstellar medium has a small-scale structure that our theories never anticipated, and that we don't yet know whether this is a local peculiarity or something universal. A local peculiarity or something universal. Think about what that means. If it's local, then the region of space Voyager is passing through is simply unusual. A particular interstellar cloud. Nothing fundamentally new to learn about physics. But if it's universal, if this hum, these oscillations, this fine-scale structure exist everywhere in the interstellar medium of our galaxy, then every model we've built to understand radio wave propagation, star formation, cosmic ray dispersion, the structure of the Milky Way itself needs to be revisited. All of it. This is the moment in the story where I'd love to hand you a clean answer. A final explanation that closes the file and leaves you with a satisfying sense of understanding, but I can't. And it would be dishonest to try. The reality is that nobody knows. Not NASA, not JPL, not the teams at Cornell, MIT, or the European Space Agency. We have the data. We have the measurements. We have the frequencies. What we don't have is the theoretical framework to interpret them. And that's where this becomes truly vertiginous. Imagine for a moment that you're a physicist in the 19th century. You're observing the precession of Mercury's orbit, a few arc seconds per century off from Newton's predictions. A tiny detail. A curiosity you note in the corner of your mind and set aside, because Newtonian mechanics explains everything else so beautifully. Then Einstein arrives and shows you that tiny discrepancy wasn't a curiosity. It was a clue. The symptom of a physics far deeper than Newton could reach. General relativity, an entire revolution in our understanding of the universe, hidden inside the precession of Mercury's orbit. So, what is the interstellar hum of Voyager hiding? Some physicists are beginning, cautiously, to suggest these anomalies might connect to a property of the quantum vacuum that our cosmological models don't properly account for. The quantum vacuum is one of the most unsettling ideas in modern physics. In quantum mechanics, the vacuum isn't empty. It's constantly threaded by energy fluctuations, particles appearing and disappearing in infinitely brief moments. Zero-point energy. And this zero-point energy is measurable. It has real effects. The Casimir effect, for instance, where two conducting plates placed extremely close together attract each other slightly because of differential quantum fluctuation pressure on either side. But our calculations of quantum vacuum energy density give a result 120 orders of magnitude greater than what we actually observe in the universe. 120 orders of magnitude, the largest discrepancy between theory and observation in the entire history of physics. What if the interstellar hum Voyager is measuring is, in some way we don't yet understand, a manifestation of this vacuum energy at cosmological scales? What if Voyager is detecting something that bridges quantum mechanics and large-scale cosmology? Two domains that modern physics has never managed to reconcile. I say if, clearly. This is a hypothesis, not a certainty. But it's the kind of hypothesis that deserves to be stated. There's one more thing I want to tell you before we reach the end. Something not in the publications, not in the press releases. In 2022, engineers at JPL began receiving data from Voyager 1 that corresponded to nothing, not an unknown signal from space, not a mysterious alien transmission, no, telemetry data from the probe's own systems. The onboard computer of Voyager 1, a machine whose processor was designed in the 1970s and whose total memory is less than 70 kilobytes, yes, 70 kilobytes, had been sending data from a memory register that should have been inactive, a corrupted register. For 5 months, from December 2021 to May 2022, Voyager 1 sent uninterpretable data, and the engineers, 23 billion kilometers away, with a communication delay of 22.5 hours each way, had to figure out what was happening inside the circuits of a 45-year-old computer. And they did. They identified the corrupted memory segment. They reorganized the code to route around the faulty register. In May 2022, coherent data resumed. But here's what struck me about this episode. For 5 months, the probe was sending data that appeared random, or what we assumed was random. It took understanding the software problem to correctly interpret that data. So what if some of the anomalies Voyager is detecting aren't unidentified instrument errors, but real physical phenomena being misread? Because we don't yet have the conceptual framework to read them correctly. Interstellar space is vast, unimaginably vast. Voyager 1 is currently in what's known as the Oort cloud, the great sphere of comets at the periphery of our solar system. Except it will take another 300 years for the probe to reach even the inner edge of that cloud, and 40,000 years to cross it entirely. 40,000 years. And the nearest star to our sun, Alpha Centauri, 4.2 light-years away. Voyager would reach it in 73,000 years at its current speed of roughly 17 kilometers per second. I say this so we can grasp that Voyager, for all it has accomplished, has barely crossed the threshold of our cosmic home, the front doorstep. And already, at the doorstep, physics isn't behaving as expected. What lies further in? I want to close with something. Not an answer. I don't have one, and neither does anyone else. But a perspective. For thousands of years, humanity has tried to understand the universe by building models, simplified representations of reality. And every time an observation contradicted a model, one of two things happened. Either the model was adjusted to fit, or the model collapsed, and something new emerged. Ptolemy gave way to Copernicus. Newton gave way to Einstein. Classical physics gave way to quantum mechanics. Every revolution began with an anomaly, a small detail that didn't fit. That bothered people. That serious scientists set aside saying, "It's just a curiosity, it's not important. We'll find a technical explanation eventually." And then one day, that curiosity became unavoidable, and everything changed. The interstellar hum of Voyager may be a local curiosity, a poorly understood plasma property, an unidentified instrumental artifact, maybe. Or maybe it's the next crack, the crack in the wall of our understanding of the universe. Still invisible to most people, present for years in the data, persistently there and growing. There's something deeply unsettling and deeply beautiful in what Voyager represents. We launched 2 small metal objects into infinity, with instruments built in the 1970s, with no ability to repair them, with no idea what they'd find. And those 2 small objects, 47 years later, are telling us, politely but firmly, that our understanding of the universe has gaps. Not errors. Gaps. Empty spaces in our knowledge. And perhaps that's the deepest lesson Voyager carries. Not the photographs of Jupiter. Not the golden record. Not the engineering achievement. This. That the universe is larger, more complex, and more mysterious than anything we've been able to imagine. And that this 900-kilogram probe, powered by the slow decay of a radioactive metal, dying quietly 23 billion kilometers away, is still whispering truths into our ear. Truths we don't yet know how to read. The question isn't what Voyager has detected. The question is whether we'll be ready to hear the answer when it comes. There's a question NASA engineers still can't answer properly. Not because they lack the words,